This is VLSI data conversion circuits, lecture 55. In the last class, we were talking about current steering DACs. Today we will continue along in that direction. So, as we were discussing the last time around, the basic idea behind a current steering DAC is to have a tail current source of a differential pair being driven by complementary signals, and if D is a logical high, D bar is a logical low, in which case this current gets steered towards the left and vice versa. Okay. So, if this is VOM and this is VOP, then you can combine a whole bunch of current sources, right. You can add them up using Kirchhoff's current law by connecting them together, and this way, depending on the digital code D, you will get an output current which can be converted into a voltage in any number of ways. The simplest way is to simply pass these currents through a resistor, all right, or you can go into a transimpedance amplifier type structure where you have an op amp based feedback loop and you can convert that current into a voltage. Now, for an n bit DAC, you have a 2 to the n current sources. Okay. These current sources are each assumed to be I, and you can address these current sources in many ways, as we were discussing the last time around. They can all be addressed in a thermometer fashion, or they can be addressed in a binary weighted fashion or some via media, where you can use the knowledge of the requirements on the DNL and INL to go and choose the appropriate degree of segmentation. But the bottom line is that the total amount of current that you need to steer one way or the other remains equal to 2 to the n times I, right. Now, for a input code M, whichever way you decode the digital data and supply them to these current steering cells, there will be M current sources eventually steered towards the left, and two to the n minus m current sources steered towards the right. Okay. And if we assume that we have a voltage to current conversion which is simply based on resistors, then VOP will be VDD minus 2 to the n minus m times I, VOM is VDD minus m times I. So, VOP minus VOM will be my R VOP minus VOM will simply be MIR times 2 minus 2 to the n times IR, which is IR times 2m minus 2 to the n. Okay. So, when all the current is flowing towards one side, which will happen when either m is 0 or when m is 2 to the n, okay, or 2 to the n minus 1 actually, right, you will find that the output of the DAC will reach 2 to the n times I, the differential output is 2 to the n times I times R plus or minus, at mid chord the output will be 0. Okay. Now, unfortunately, each of these current sources will have a finite output impedance, and therefore, what happens is that this current source is not ideal. Please recall that as we were discussing the last time around, these current sources are actually implemented using MOS transistors, and an example of a good current source where the output impedance has been enhanced is to use some kind of cascode. Okay. This is not a particularly good choice of biasing the cascode voltage, but I hope you get the idea. In your other classes, I am sure you have seen better ways of biasing the cascode where you do not waste so much headroom, right. I am assuming that you know all that stuff. In any case, whatever you do, finally the output impedance of the current source will not be infinite. You can only make it larger and larger and larger, right. And on top of this, you also have in effect another cascode, because when the current source is fully switched to one direction, the switching transistors which are 2 in number, one of them will be off and the other one will be on, and effectively if you make sure that the switching transistor does not get into the triode region, which is easy enough to do, all that you need to do is make sure that VDD is high enough, right. Okay. So, if the switching transistor is in the saturation region, then effectively the switching transistor also acts like a cascode device, right. It is another common gate stage, and therefore, the effective output impedance of the tail current source is multiplied by a further factor of GM times RO. So, the effective output impedance is of the order of RO from the lowest transistor times GM RO the whole square. Okay. Of course, the ROs of all the 3 transistors will not be the same, but this is intended to give you an idea of the order of magnitude of the output resistance. Is this clear? So, in other words, what we have is not really this scenario where we have an ideal current source and where in the ideal case we have two current sources which are digitally controlled, both of them pump current into the same resistor, and we are looking at the difference between the outputs of these the voltages across these resistors. In practice what we have is that on one side we have a conductance of value. Conductance, I mean the idea behind using conductance is that you do not have to keep carrying 1 by R's all over the place. So, what is the output conductance of this Mi current source? If you call the output impedance of each one of these current sources, let us assume that each of these current sources has an output conductance G, right. This G is of the form 1 by some gm Rho square times Rho in this particular example. Okay. So, if you have m current sources coming together, the output conductance will be m times G, and you have 2 to the n minus m current sources coming together, you will have 2 to the n minus m times G. Right. So, this is a model to understand what happens with finite output impedance. So, what is, I mean before we get into the details, what do you think this does? Well, that is okay. Can you guess what this will do to the output characteristic of the DAC? Is it a linear effect or is it a nonlinear effect? Why is this a nonlinear effect? Why is this a nonlinear effect?
The error in the mth code is dependent on that.
Yeah. So, as you can see, the differential voltage depends on the differential current, okay, which is a linear function of m. Finally, you want the output voltage to be a linear function of m, that is what a linear DAC will do, correct. So, as far as the Norton equivalent or the short circuit current is concerned, that seems to be quite linear with the digital code m. The problem is that the effective load resistance is also code dependent. So, when you multiply this current with the output resistance which is code dependent, the characteristic becomes nonlinear, all right. So, the output voltage this is m I is 2 to the n minus m times I, and this conductance 2 to the n minus m times g. So, you can convert this into a Norton equivalent, right, and okay. So, I am not going to go over the details of the calculation here, I think you can do it yourselves. The bottom line is that the load resistance depends on code. So, output voltage VOP minus VOM is non-linearly dependent on input code, which means this causes DNL slash INL. You can of course do the math and find what the DNL or INL will be for a given G, correct. Okay. So, but one thing we can say with certainty is that as G times R, okay, tends to 0, the INL and DNL will also tend to 0. Okay. Why G times R? Why not simply G? Pardon? Okay. So, finally, you are only interested in how much of this current passes through these two resistors, right. So, for a given G, if the R or the conductance of the load resistors is much smaller, then a larger fraction of this current flows through the load, thereby which is equivalent to saying that a smaller fraction flows through these conductances and the current through these conductances is responsible for the error, correct. So, as a limiting case, if the load resistance was 0, regardless of what G was, all this current would flow into R, correct, which means that the output voltage will be linear, you understand. So, in other words, depending on the DC, DNL and INL requirements and the desired resolution of the DAC, one can go and figure out what the ratio of the output impedance of the current sources to the load resistance must be. Okay. So, this determines all right. So, the next thing is the matching of the current sources itself. As we saw the last time around, the matching of the current sources along with the choice of the segmentation determines the sigma of the DNL and INL, correct. So, it turns out that the Vt of the transistor is a random variable, and with some mean Vt naught and a delta Vt which is assumed to be Gaussian with a sigma delta Vt of which is of the form A Vt divided by square root of W times L, okay. And assuming that the transistor current I d is written as half mu n C ox W by L times VGS minus Vt the whole square. The fact that this this Vt is varying randomly around a mean means that the current ID will change in a random fashion, and unfortunately it also turns out that this so called mu n C ox W by L, this beta factor, is also a random variable, okay. So, there is also this is often called the beta factor, and the sigma of beta is nothing but some A beta divided by square root W into L, okay. So, the change in the current due to a change in beta and due to a change in Vt is given by dou Id by dou beta times delta beta plus dou Id by dou Vt times delta Vt, okay. And this is nothing but half into VGS minus Vt the whole square all right times delta beta plus dou Id by dou Vt is nothing but by definition is the same as minus Gm, correct. So, and Gm is nothing but 2 Id by VGS minus Vt times delta Vt. Okay. So, sigma of delta Id or sigma square of delta Id is nothing but squared sum of these things. So, it often makes sense to do. Finally, we are interested in the percentage change, the absolute change in the current is, I mean, it is relevant, but it is only half the story. You need to compare the absolute change in the current to the actual current, right, so that you have something which is dimensionless, and this goes into all those DNL/INL calculations that we saw earlier. There we saw that with respect to resistors, here it is with current sources, but the change in the unit element is delta I by I, which has got some variance, isn't it? For different devices, the the properties of the equations of the device mandate different expressions for this sigma of delta I by I, but otherwise beyond this the calculations you will do to determine what this variance or mismatch factor must be in order to achieve a given DNL and INL still remains the same. So, let us do, so delta ID by ID is nothing but 1/2 beta into VGS minus VT whole square, and this is 1/2 beta into VGS minus, this I will just call this ID, and we see that this goes away and this goes away, leading to delta ID over ID is delta beta by beta minus 2 delta Vt by Vgs minus Vt the whole square. I am sorry, Vgs minus Vt. Okay. And this makes intuitive sense, all right. Why do you think this expression makes intuitive sense? This is telling you that if you want, let us say for a given current, you want to reduce the error in the current, okay, for a given delta Vt. Let us say the threshold changes by a certain amount. This expression is telling you that for the same current, if you increase the gate overdrive voltage, the error in the, or the mismatch in the in two nominal currents will be smaller if Vgs minus Vt is larger. So, why do you think this makes intuitive sense? Now, what I am saying is, yeah, it's all fine that this comes out of the math, right, but the question is, why does this make intuitive sense, or does it make any sense at all? Yeah, that's correct, that's what comes out of the math, that's correct.
If current is more, marginal current can be VGS minus VT is more, current will be more.
No, we are interested in for the same current, right. It makes sense if you want to have the same unit current, only then you can compare things reasonably. Delta Vt of course is acts like an incremental VGS, that is correct. So, what?
Same current if ID is equal to VGS minus VT into W over. So, if VGS minus VT is smaller, I need a larger W by L. So, which means the ID is more.
No, what I am getting at, or what I am trying to point out is, why do you think this Vgs minus Vt appearing in the denominator makes sense? Okay, let me, so let us say you have two transistors, let us have argument say this is W by L and this is 1/4 W by L, right. Both of them are biased so as to have the same current. So, what must this voltage be? Pardon? This voltage, if this is Vt plus delta V, this must be Vt plus 2 delta V. You must have twice the overdrive in order to result in the same current. Now, let us say the Vt changed by a little bit, this is delta Vt, this is delta Vt. Clearly, this drain currents in both the transistors will change. Which of them will have a larger change, or which is larger, delta I1 or delta I2? Delta I1. Now, why does that make sense? No. Yeah, okay. Yeah, the W by L is higher is one way of looking at it. Alternately, you can say that the overdrive is smaller for the transistor on the left. So, the transconductance of the transistor on the left is higher, which means that for the same change in the threshold, the change in the current will be larger for the transistor which has a higher transconductance. You understand? So, in principle, if you want to be immune to threshold mismatch, you should make this transistor infinitely small and have an infinitely large VGS minus VT, right, in which case a small change in the threshold will mean no real change in the current. Okay, in practice, of course, you will always be limited by headroom, isn't it? If you want to have a very large VGS minus VT, it means that somewhere, I mean, this transistor needs at least VGS minus VT to remain in saturation. So, if you go on increasing VGS minus VT, you will find that you use up all your headroom just to maintain one device in saturation. So, that is a practical limit. So, when you are designing a current steering DAC, for example, if you have resistive loads, the peak to peak output swing is some specified quantity, right, which, and the load resistors are also specified, which means that the sum total of all the currents is known, which means that the unit current cell's current is known, right, and you want to keep all the transistors in the saturation region, including the switches, right. I mean, one straightforward argument to say why you want the switch transistors to remain in saturation is that we saw just now that you want to make sure that the output resistance of each of these current sources is as high as possible. So, that is one reason to make the switch transistors operate in saturation. You understand? So, once you know the peak to peak voltage swing at each of the output nodes of the DAC, it then means that because you want to maintain at least 3 devices in saturation, right, the supply voltage minus the peak to peak swing must be split in some way across 3 devices, right, which will boil down to the fact that for a given supply voltage there is only so much VGS minus VT that is possible across the lowest device, which is what sets the current, all right. So, for that VGS minus VT, if you find that the mismatch is too high, or this delta I by ID is too high, then there is no way out. For a given threshold VGS minus VT, you simply have to go on reducing this delta Vt, and how do you go on reducing delta Vt? You keep W by L the same, right, and go on increasing W into L, and that can be done by simply scaling W and L by the same factor. You understand? So, the sigma delta ID by ID is, sigma square is given by sigma square of delta beta by beta plus 4 by Vgs minus Vt the whole square times sigma square of delta beta. So, sigma Vt, as we just discussed, or sigma delta Vt is A Vt divided by square root W by L, square root W times L, and what are the units of A Vt? I mean voltmeter, often quoted in millivolt micron. Okay. So, sigma square Vt will be A Vt square divided by W. Okay. So, this will be A Vt square times W into L, and sigma square delta beta by beta will also be some A beta square divided by W times L. Does it make sense? Okay. So, if for the same current you want to reduce the mismatch, or in other words if you want to reduce this delta sigma delta ID by ID, the only way you can do it is to keep W by L the same and keep increasing W times L. All right, assuming that you have maxed out the Vgs minus Vt. Does it make sense? All right. So, the next thing is to try and figure out what happens when the current cell is actually switching. In other words, assuming this current is I1 and this current is I2 and this tail node is denoted as Vx, the voltage here is probably doing something like this, while V left I will call it and V right, okay, and VR is doing. So, can we comment on what happens to Vx? What is it way before this transition? No, yeah, sorry, yeah. So, way before the transition, all the current I will be flowing through the transistor on the right. So, the voltage will be this voltage will be VR, the difference will be Vt plus square root of 2I by mu n Cox W by L. Okay. If I now call this delta V, I am going to say this will be Vt plus delta V. And way after the transition, after all the transients have settled, the voltage must remain. All the current is flowing in the left transistor, assuming the two transistors are identical, the voltage must remain Vt plus delta V. So, the question now is what happens in the middle? What do you think will happen when we are at this point where the two drive waveforms cross each other? No, it will not be the average value of both of them are carrying the same current. So, the difference you have to worry about is between here, how much lower than this waveform, the average value of VL and VR will the node Vx go to. When both the transistors are carrying current, what happens to their overdrives? The overdrive will go down by a factor of root 2, and therefore, what will happen will be that the voltage will be VR plus VL by 2 minus Vt minus or Vt plus delta V by root 2. Does it make sense? And So, the Vx waveform, if I exaggerate, draw this in a very exaggerated fashion like this, this is Vr, this is Vl, okay. What must be the what will be the difference between Vr and Vl? I mean, or rather, can you comment on the difference between Vr and Vl in relation to delta V? What is the idea behind having Vr and a large difference between Vr and Vl? You want to make sure that the current completely switches to one side, which means that the difference between Vr and Vl must be at least delta V, right. In practice it will be several times larger. So, let us just assume for argument's sake that this is say 3 times delta V, right. Definitely a safe value to choose, given that this will completely switch the current from one side to the other. There is nothing holy about 3, I just chose it. So, which means that this Vx before the transition occurs is the average of Vr and Vl minus so this difference will be Vt plus delta V all right. And this absolute voltage is Vr plus Vl by 2 . Okay. And the same thing happens well after. So, this difference is also assumed to be P delta V. At the cross point, what happens? The difference will be, or Vx will be Vt plus delta V by root 2 from this voltage. So, do you think it will be lower than this or higher?
Vt plus delta V is with respect to the begin or from Vr?
You tell me. Oh, sorry, yeah, that is correct. This is Vt plus delta V from Vr, that is correct. Thank you. all right. Okay. So, from the average, how much lower than the average is this? Let us call this V average. This will be V average minus V r is nothing but V average plus 1.5 delta V, and this will be minus V t plus delta V. So, this is V average minus V t plus half delta V. Does this make sense? Whereas the middle voltage will be what will be the voltage V x at the cross point of the two waveforms? It will be V average minus V t minus delta V by root 2, correct. So, what happens? So, do you think the waveform in the middle will dip or will rise? This voltage will be V average at cross point. V x must be V average minus V t minus 0.7 delta V. So, what happens in the middle? Will it go down or go up? It will go down. So, without getting into the details of the waveform, at least one thing you can say is that the waveform actually dips. You understand? All right. So, in the next class we will see what happens. So, please bear this in mind that during the transition, assuming perfectly symmetric waveforms, okay, so that the cross point occurs exactly at the average of V r and V L, the voltage at V x actually undergoes a dip like this. This is assuming that everything, I mean all this calculation was done assuming that everything is within quote static. It is as if V L and V r are moving so slowly that the currents through all, I mean in practice there will be currents at this, there will be additional current in apart from I due to what parasitics? I mean if this voltage is changing with time, then the parasitic capacitance at that node will cause a reactive current, right, which will be in parallel with I, okay. But all our calculations so far based on, I mean for voltages have all been based on DC considerations, which means that we have neglected the current through the parasitic capacitances, okay. So, in the next class we will see what happens when these parasitic capacitances are considered, okay. All right.